Okay, so far we talked about flux and we learned about the equation, but we didn't really apply them to the problems, and we will do that in the lecture. And I will also show some simulations that will really help you visually see, because again, this concept is very abstract. So we need to understand flux before we understand Gauss law, and in this section we will apply Gauss law, and we will identify that charge outside a Gaussian surface makes no contribution to the net flux through the closed surface. And then we will only look at the charge enclosed by the closed surface or the Gaussian surface. And we will derive the expression for the magnitude of the electric field of a charged particle by using Gauss law. And we'll identify that for a charged particle or uniformly charged sphere, Gauss law is applied with a Gaussian surface that is a concentric sphere. I briefly talked about this already, but again, there are several symmetric cases that we are looking for, not many, so we will look into them in a few times so that the concept is clear. So why do we care about flux, first of all? Because flux is related to, so we're going to take some notes here. Let me make sure my writing is clear. Flux is related to the charge within the closed surface. And we will call that enclosed charge. So we know that so far Gauss law tells us the flux, right? Flux is phi in Greek letter, and it is, then we will say, the enclosed charge over epsilon naught. Okay, so that ENC is the stands for enclosed. So you're only looking at the enclosed charges within your Gaussian surface. So you need to show your Gaussian surface so you can see how much charge is enclosed. Sometimes we will need to do calculations to find that. Sometimes it's going to be so easy to see it. And epsilon naught is the same permittivity constant. We have the value in the equation sheet. And we can find the flux if we know how much charge is already enclosed. If we don't know, sometimes that we don't know how much charge is enclosed, so whatever is the unknown, we have also this relation. And again, this is the integral over the Gaussian surface, because dA is your differential. So that's your guide. You're integrating over the Gaussian surface, and it is enclosed surface, right? That's why we have that circle on the integral, and that kind of reminder for us that our Gaussian surface should be closed surface. And since this is also flux, we can say that this integral is equal to Q enclosed over epsilon naught. Okay, so this is our relation. These are both equal to flux, and that's the electric flux, because we're talking about electric field. Okay, here the charge enclosed can be just, if we have several, let's say, particles, charged particles, you just add them up, but only the ones which are within the surface. So all the charges enclosed by the surface. And if you end up with having negative flux, because you are not adding those charges in absolute value, again, you're just adding them up. So if they're positive, you're having positive value in there. If you're negative, you're keeping the negative value, okay? That's a little different than the Coulomb's law. Because the sign of flux will tell us whether it is inward flux or outward flux. So we are keeping the sign of the charges here. Okay, so that's an important point. So if the flux is less than 0, that implies the total enclosed charge being negative. Okay, if flux is greater than 0, that implies the total enclosed charge being positive. So it's really the direct relation between this side of the equation versus that side. Epsilon naught is always positive. It's a constant. And depending on the net charge, total charge enclosed only, that will tell you if your flux is positive or negative. And we will see this in the couple examples coming up. I'm going to show some of them in the video, and we will do more practice in class as well.